For the third experiment called Bullseye, its purpose is to investigate the horizontal and vertical components of motion and to predict the landing point of a projectile. In this experiment, we used these following materials: a graph paper combined with another graph paper in order to form a ramp, marbles, a cardboard cup, tape measure, and a stack of coin wrapped in tape hanged in a yarn in order to substitute a plumb line, and also a stopwatch. The group found that the average time for these runs was 0.19 seconds. By applying the formula distance AB over time, the group were able to determine the average horizontal speed across these three runs. Here is the data for the three runs we executed. We then calculated the horizontal speed by using the formula distance AB over time, which is 105.26 centimeters per second or 1.0526 meters per second. The group answered that the height of the can plays an important role in the vertical distance. Since the height of the cup represents the vertical distance the ball will travel from point B to the bottom of the cup. Ignoring the height of the cup can lead to miscalculation, leading to failing the ball to fall inside the cup. To find the vertical distance that the ball travels from the end of the ramp to the cup, we measured the height of the cup, which is 8 centimeters, and subtracted it to the height of the platform, which is 30 centimeters, giving us a vertical distance of 22 centimeters. Applying the relevant data discussed earlier, the group determined that the time t required for the ball to fall from the bottom of the ramp and reach the can. Here's the equation for vertical distance. H is equal to 1.5 gt squared. We then were able to get the final time, which is 0.21 seconds. To complete the experiment, the group predicted the range of the ball, which represents the horizontal distance traveled by the projectile. First, the students proceeded to place the can on the floor at the spot where they had predicted it would catch the ball. Then, they also calculated the range by using the equation distance is equals to speed times time. Here's the data of our average time, predicted range, and our horizontal speed. By using the formula distance is equal to speed times time, we were able to get the range of the trajectory of the ball, which is 0.23 meters, which surprisingly is parallel to the predicted range of the students. The group stated that there is no difference between the actual range and their predicted range. We used two different approaches to figure out the range. One where we manually measured the distance from the launching point to where we thought the cup would be, and the other where we calculated it using the formula x is equal to vt, since there is no difference between the accepted value and the measured value. We then conclude that there is 0% percentage error. The group responded with, the first one is air resistance. The air resistance can affect the trajectory of the ball, causing it to drift from the expected path. The other reason is the misalignment of the cup. This can lead to the ball missing, not landing to the cup due to the cup not being correctly positioned. The group answered that the air resistance, which acts as a resistive force against the motion of the steel ball, played a role in this experiment. The faster the ball, the more air resistance it had to overcome. As a result, the ball's range was impacted. Thus, drag or air resistance somewhat influences the ball's horizontal motion. However, a faster speed helps overcome air resistance more effectively, resulting in a longer range. Our group concluded that this experiment shows the connection between the initial speed and the range of a steel ball, rolling down a ramp and landing in a can. The properties of the platform and the surface are essential in measuring and predicting the landing point of a launched object. Additionally, we have observed the different factors that affect the trajectory of the ball, and the range of the ball is actually influenced by its launch speed. Hence, the range increased with higher initial speeds, demonstrating that horizontal velocity influences projectile motion. This experiment has provided our group with knowledge about the principles of projectile motions, kinematic equations, and how to estimate and calculate object motion in a controlled setting. Additionally, through this experiment, we were also able to observe the importance of the vertical and horizontal components in measuring and predicting the trajectory of two-dimensional motion.